Given a staircase with n steps, how many ways are there to reach the top step if you can only move 1 or 2 steps at a time? In the previous video, I went over how to solve this at a high level, and in this video we're going to do an actual implementation. And the approach I'm going to use is to start with a recursive solution and to keep making improvements to it until we reach the optimal solution. And the idea behind doing it this way is that you can then use the same method on more difficult dynamic programming problems. So if you're just coming here directly and you didn't see the previous video, that's why I'm doing it in this sort of roundabout way instead of just typing out the optimal solution for you to look at. So let's get started. We're going to make a function called ways, which is going to return the number of ways to reach the nth step. And let's come up with some inputs and expected outputs so we can test this function. Okay, so for these given inputs, these are the outputs we expect. And just to remind you, these are the base cases. From the very beginning of the staircase and the first step, there's only one way to reach those. So let's make these calls and then we'll print out the value. So for the value 5, we expect an output of 8. And we'll just write this to the console. And so what we want to do is start with the recursive solution, which we went over in the previous video. We just are going to make 2 recursive calls and add them together. So that'll be from the previous step and 2 steps before. And then to break out of the recursion, so this doesn't go on forever, we need the base cases, which are if n is equal to 0 or 1. And we'll just use the less than or equal to operator for that. And in that case, we just return the value 1. So at this point, when we execute this program, we should expect an output of 8. And this seems to work. So now what we're going to do is we're going to show that when you increase the size of this argument, because we are doing a brute force number of function calls, that this is not going to actually return in time. The program's just going to hang. And we can actually put a little variable up here just to show that this function's being called a whole lot of times. So to fix this running time issue, what we're going to do is we're going to introduce a cache. And the idea is pretty simple. What we're going to do is we're going to make a variable out here called cache. And we could use an array because the keys are basically just numbers, but I'm going to use an object literal just so we can see what the keys are explicitly. And basically the idea is the keys are going to be the n values, and the values are going to be the result of calling ways of n. And that'll prevent us from making multiple calls. So what we're going to do is we're just going to make sure if this was called previously, that we're just going to return the value that we've saved. And then all we have to do is at the very end of the function, before we return the value, we just have to save it into the cache. So here what I'm going to do is I'm going to split this into some variables so that we can reuse them in more than one line. And first we're going to save it into the cache for the argument of n. It's the sum of these two values, and then we're going to return it. Now when we run the program, what should happen is it should actually return a value, although I'm not sure what the 500th Fibonacci number is. But it did return in time, which means that we're making progress. Let's just change this to 5 and make sure that the output's 8. And it is. So at this point, this is a working algorithm. It does find the right solution, and it does it in a reasonable amount of time. But the problem is at this point is that we are using a ton of space. So if I just log out the cache at the very end here, you can see that we have all these values within the cache, but really at any point we're only referencing the 2 previous values, so all this extra space is actually wasted. So one thing we can do is convert this to a bottom-up solution. So you can think about it as if each function call is kind of pointing backwards to two previous function calls, and then we're going all the way back to the bottom, and only once we reach the bottom do we start building up this cache. But it's within the cache that we actually have the values that we're concerned with. So the idea is that we're just going to basically ignore the recursive function calls that build up the cache, and then just think about the cache as sort of the main object, and we're going to build up from there. So let's convert this to a bottom-up iterative solution. So what we're going to do is we're going to move this cache inside the loop, and basically, like I just said, instead of using these recursive calls to pass in the values and then build it up, we're just going to reach directly into the cache. So what we're going to do is, let's start by adding the base cases into the cache. That's usually something that you need to concern yourself with at the beginning of the problem. So we'll add the base cases of 0 and 1. And then it's also common to then start directly after those base cases. So let's start with an index of 2. And we're going to have to go up to I equals n. And all we're going to do is, instead of, like in the recursive solution, we referenced the two previous values. So now we're just going to do basically the same thing backwards, where the ith value is going to reference the two previous values. And that's all you're going to have to do, because we know that by the time we reach any of these indexes I, that we've already hit I equals 1 and I equals 2. And when we start with I equals 2, we already have these two values as the base cases. So let's, before I return it, I think I'm going to log it out here. And this should return the same value for 50 that it was returning before. And there it is. So this is working, and this should return 8. Just sanity check real quick. Yep. And so you can see here that I did convert this to bottom up, but we are still using a linear number or linear size. We're still saving all these values when we really don't have to. And so now we're going to make some space saving adjustments to this. So one thing we can do to save some space is basically just wrap around, kind of use like a circular buffer, so that as we start putting elements into an array, instead of putting the fourth element here, we'll just loop back around and start back here again. And then we'll put in the fifth element in the cache and the sixth element in the cache, and just keep going like this. And that seems kind of tricky when you look at it like that, but really all you have to do is use the mod operator with the size of the array that you want it to be at the end. So we'll use 3 values, so we can have the reference the two previous values and then have the current value. And this is something that it's helpful to, it's like a good thing to use once you already have a working implementation that just uses too much space. It's probably not so good if you're just trying to figure it out in the first place. And so I'll show another way of doing that, but the thing to remember when you're doing this is just anytime you index into the cache at all is to use the mod operator, and it'll just work. So this should still work, but now have a size of 3. Yep, and you can see that if we keep increasing the size of this thing, that it'll just keep adding these values in. And even for really big values, it should just work like that. Yep, so at this point we're actually at the optimal solution. We have constant space because we're only using a cache with 3 elements in it, and it's linear time because it loops through from the beginning from 0 up to n, to the size of the number of steps. And just for the sake of completeness, one thing I want to do is convert this to a slightly, possibly easier solution, which is just instead of using a cache of size 3 to just use a couple variables. That's something you'll see a lot, especially if you only need 2 or 3 variables. So let's just convert that here. So instead of initializing the cache with 2 variables, we'll just start with, I guess, we can call it, actually I guess these have to be let variables. We'll have like a current value for whatever the current step is, and we just need one variable for the previous step. So these are like the base cases. We don't need the caches anymore. And within the loop, then all we have to do is update the current to be the previous step basically, plus the step 2 before, which will be saved in the previous variable. And then we also have to update the previous to equal the current from this round. But because we just modified it, we have to just use a temporary variable. So we'll just take I like using the word snap for like snapshot of the current value. And then if we return cur, that should be the answer. And this is kind of what I would expect to see if you just looked up the solution somewhere else. But the reason I went through this whole thing is basically that on more difficult problems, it helps to have this kind of approach where you start with a recursive solution and then you introduce the cache and then you think about the cache, convert it to a bottom-up but not space optimized, and then you start thinking about how to optimize space. And if you take that approach to more difficult problems, I think it's a lot easier. And so let's see, does this actually work? Yeah, so it's the same values. So at this point, this is the solution, and in the next video, what I want to do is start introducing some more complex problems. So I think the next video, what we want to do is we'll have a similar problem where we are asking the question, how many ways are there to get from the top left of a grid, of a matrix, to the bottom right, where from each cell we're only allowed to go to the right or to the left. And that problem is a lot like the step problem, because instead of coming from the previous step or 2 steps below, we're either coming from the top or from the left. And then the complication that makes it harder is just that we're going to be using a cache that is, we'll start with a cache that's going to be 2-dimensional, because it's going to basically have to have all the cells that we possibly can visit. And then I'll show that we can actually get it down to just a single row. And that's what's going to be in the next video.